Hello and welcome to a quick presentation on the a concept of a combination of a series of concepts that result in some really quite startling advances in computing. So to begin, I am the author of the curator of the SimpleV specification for the Power ISA, which applies a strict risk paradigm to a vector ISA by utilizing prefixing. The simplest way to explain that is here we would have a scalar instruction set where you just do straight fetch, decode, issue, and execute. SimpleV inserts a loop in between the decode and issue phase. It should be fairly self-evident how that would be multi-issue executable, and how predication can be inserted on top of an existing scalar ISA, which does not itself have predication, as it simply says it tells of whether to skip that unit or not. And then on top of that, we've worked out that you can do hardware looping. This loop 0 to VL minus 1. You can specify matrix multiply schedules which issue, multiply, and accumulate, utilizing the where are we? Utilizing it's in another PDF. I'll show it in a bit further down. You can utilize the schedule to multiply and accumulate the accumulate register becomes an accumulator, and you can do arbitrary in-place matrix multiplication, not limited to radix 2. But that's a quite simple thing, relatively speaking, compared to what I'm proposing here. There are the advantages of that approach are that you end up with much more complex programs. They save a huge amount of power. If you've ever seen how in a PackSimD instruction set, if you want to do a 3x3 matrix, you have to repeat the data across the 4-way SIMD register in a loop unrolled fashion, which is horrendously inefficient. Whereas for matrix multiply, it's just in SVB64, it's 3 instructions. So there were 2 pieces of work that I spotted, which are very significant. So 3. One was something called ExtraV, and ExtraV is it's an accelerator system where you have processing managed by OpenCAPI close to the memory, and there is a because it is all scheduled, deterministically scheduled, you can have the workers, the ExtraV workers, down at the near the memory, pre-processing or pre-vetting in a fully deterministic fashion the data that is sent to the main CPU. This is some research was done a few years ago, but surprisingly it has not made it to mainstream. I have no idea why. It's an extraordinarily innovative idea, and not least because it is node graph walking. It is full. It does a full node graph walk, and basically it's a type of map reduce. It's absolutely brilliant, but it's putting the pieces together here. It's quite an important strategic link in the chain of what I'm proposing here. Now, the other piece of work that I spotted was something called Snitch. Now, Snitch is astounding. It reduces power consumption by 85%. When you think of proposals that are made for computing architectures, you think maybe 5%, maybe 1% is great, 5% is fantastic, 10% is something to massively celebrate. 85% power reduction is just astounding. And what they've done here is they've scheduled loads and stores that go, instead of going into through level 3 to 1 cache process register file, they go into FIFOs. And because you're using the main memory, those are quite slow. So what they've done is done time division multiplexing, so that you have 8 simultaneous banked loads and stores, and that way you can keep the floating point unit busy. But the input it uses tagged registers for a floating point multiply and accumulate, and it doesn't go, the result does not go into the register file. It goes directly back out again to a second FIFO, and again is using deterministic schedules to avoid having to put things into the register file or put it into the level 1 cache. And again, it's close to memory processing, but not. Now, combined with ExtraV, ExtraV has a filter on those FIFOs in effect. So the other thing I noticed was something called zero overhead loop control. And this is another astounding reduction in power consumption, but also in completion time. The motion estimation algorithm for MPEG video is completed 43% faster by using zero overhead loop control. One thing that's slightly complex about this, though, is that they had to use what's called a context selection to use a context-free grammar. So you wrote the program in C, you run it through a preprocessor which spots the basic blocks and creates a context-free grammar. But the savings here are astonishing. But the important thing about it is it's actually remarkably similar to what SVP64 already does. So what I decided to do was to combine all 3 of these. And here you can see we've got, this is your main CPU. We would have a 3-way bridge PHY with the DRAM, and these processing elements down here basically run the exact same power ISO with SVP64 with zero overhead loop control, snitch-like and ExtraV-like processing capability with coherent, deterministic, scheduled algorithms running that we can decide whether to run them on the CPU or whether to run them on the processing element transparently. So here's how you would do it if you had the main CPU. You have your loop, you have a load, you have a test. Is the answer 0? Because what we're looking for is a sparse matrix, a massive sparse matrix, or any other algorithm similar to it, where if you're loading elements that are 0 in a matrix multiply, you're wasting your time. But if you have to pull that all the way through the level 1, level 2, level 3, and in some cases level 4 cache, you've really wasted power and time. But that's what a standard CPU does. It's unavoidable because we're looking at, standard Harvard architecture here. And it goes in, you do the load, goes into the register file, test it for 0, you do the multiply and accumulate, you store it in the reg file, and then you have the store instruction, and then you increment and you go back around the loop. If you do that in the snitch style, your load and store doesn't go into the register file. You know that you're doing a matrix multiply, you're doing a deterministic schedule, so you know exactly which things are going to load and what's going to be loaded and what's going to be stored. Even when you hit the with instructions, before you've even run the instructions, you know from the size of the matrix, exactly matrices the inputs, exactly what you're going to need to do for the next 10,000 or 100,000 or a million instructions. So no level 1, level 2, no register file. And testing from 0 can be done in the processing element. You don't send it, and because it's a deterministic schedule, you don't care. You know deterministically that if it's 0, it didn't get in. So thing, and you know it's only going to be a multiply. So the only things that you send to the CPU over OpenCAPI are the things that actually need multiplying. Maybe you put it into the register file, maybe you don't. You put it using snitch style, you send it directly back out again into a FIFO and put into an OpenCAPI FIFO this time and store it. And finally, if you really want to, you could actually put if it's FP16 small enough, you actually put, and if you can do it in parallel, you actually put the FP16 multiply unit down in the processing element, and you give the processing element a register file because it's nice and small, running and slow, and blah blah blah. And then you could do massive number parallelism, and back to this, you've got parallel processing. And then your main CPU simply becomes a coordinator of coordinator of what's happening over OpenCAPI. There is an extraordinary amount of research going on in this area, but looking at it, some of it, Samsung's processing in memory, it's touted as having a 70% reduction in power consumption and 2 times performance and increase in speech recognition. But some of these ideas from Snitch and ExtraV and zero looping muller that. We completely muller it. So there is a huge amount of potential here. That's it. Thank you very much.